Okay, guys, this is Dr. Kruse, elementary statistics, and we're going to talk about frequency tables and graphs today. So we're kind of just discussing where the standard normal distribution comes from. So this is just a set of data. It's 30 values. N equals 30 is a handy thing to put off to the side. Usually when you're dealing with a set of values, first thing you want to do is count them. So I have 30 values, 30 measurements that I've taken, and whatever I'm studying, maybe it's the average weight of an animal, or average height of something, or average number of dollars in anybody's wallet at a particular time. It's whatever you're measuring. You have taken 30 measurements, and this is just called raw data. We haven't done anything to it. We haven't organized it. Once we organize it, we're going to kind of see some patterns emerge. So we're going to construct a frequency table and turn that into a graph and just kind of observe what happens. So constructing a frequency table, if they ask you to construct it with 5 classes, they're saying 5 rows in your table. It could be 6 rows, 7 rows, whatever. But if they say classes or layers, they're just talking about rows. So I got to take all this data and I got to organize it so that I have the same number of values in each row. Well, that's actually pretty easy to calculate. We start with the lowest value, circle it. 3 is the lowest value I see, the lowest measurement that I took. And then we circle the highest value. 32 is the highest measurement that I took. Whatever we're measuring here, this is the highest one. So I'm talking about the numbers from 3 to 32. Well, how many numbers is that? Well, that's 32 minus 3. That's 29 numbers. All right. A range from low to high, that's called the range. That's a range of 29 numbers. So I need to take our range, our 29 numbers, and I need to divide it into 5 equal parts so that the same number of values are represented on each row. So a little note down here is find your class width first, how many numbers you're going to put in each row. So take your max minus your min, our 32 minus our 3, that's 29 numbers. And then however many rows you want, classes, layers, whatever they call it. So in this particular table, I want 5 rows. So 29 divided by 5, well, that's a weird number. It's 5.8. I'm going to always round that up to whatever. In this case, I'm going to round it up to 6. So I'm not going to say I'm going to put 5.8 numbers in every row. That's kind of weird. I'm going to round it up to a whole number, 6. All right, so starting with our lowest number, 3, I want to include 6 numbers in each row. Okay, it's just easiest if you just do counting it on your fingers. All right, oops, trying to put my fingers in here. Starting with 3, it'd be 3, 4, 5, 6, 7, and 8. That'd be 6 numbers. That's where we got the 3 through 8. That's 6 numbers. It's hard to do mathematically because 8 minus 3 is 5, and that doesn't really work. We want 6 numbers. You have to include, the number you start with as one of the numbers. So 3, 4, 5, 6, 7, 8. That's 6 numbers. And then 9, 10, 11, 12, 13, 14, that's 6 numbers. So the numbers 9 through 14 we'll record on the second row. And then 15, 16, 17, 18, 19, 20, that's 6 more numbers. Anytime that value occurs, we're going to record it on the third row, and so on, all the way up to 32. So now that we have a row for every value in our table, we know where everything falls. Well, the next thing we got to do is we got to stretch it a little bit, because what if we had a value like 8.3. Well, 8.3 is bigger than 8, so it doesn't go in this row. And 8.3 is smaller than 9, so it doesn't go in this row. So we have a whole bunch of decimal numbers that don't have a home. We're going to stretch these limits here. We're going to call them boundaries now. We're going to just go stretch them a half step in each way. So a half step lower than 3 is 2.5, and a half step higher than 8 is 8.5, 8.5. Stretch this down, that's 8.5. Stretch it up, that's 14.5. So we stretch each one of our limits half a step either direction. We're going to stretch that out, and now basically every number has a definite row to go to. Now maybe some of you guys are spotting the actual number 8.5 is in 2 rows, 14.5 is in 2 rows. Yes, that is a flaw. This isn't perfect, but it's close enough, all right? If we wanted to be really, really precise, we'd say this is like 8.49, and then 8.5 would go here. We're not going to get that precise for this introductory lesson. We're going to say that's good enough. Just stretch it a half step in either direction, and now we've got almost all values covered. all right, with a tiny, tiny little exception that we're going to ignore. Notes for that, class boundary, just stretch the class limit a half step each way. All right, next is midpoint, and midpoint is just the halfway point between 3 and 8. All right, we're just going to add those up and divide by 2. If you just do an average, 3 plus 8 is 11, 11 divided by 2 is 5.5. Average these two to find the midpoint, the point that is halfway between 9 and 14. Add those up, that's 25 divided by 2 is 11.5. So here's the notes on midpoint. Just average the two class limit numbers to find that middle point, the point that is in between these two numbers. All right, now finally, we are ready to deal with frequency. This is called a frequency table, a frequency distribution table. And we're finally ready to count. All right, so back to my raw data that I have not organized in any way. Back to my 30 measurements, my 30 values that are just sitting there waiting to be organized. Well, I'm going to go through here and I'm going to count how many values go into each row. I'm going to count how many values are between 3 and 8. Well, there's a couple of ways to do it. One is by using tally marks. So I could go up here and every time I see a value between 3 and 8, I would put a little tick mark here or a tally mark here. So that's no, 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 no. There's one. That's 3 to 8. Actually, I'm looking at the class boundaries. Is it between 2.5 and 8.5? But this is close enough. All right, so 3, yeah, that goes in row 1. I would put a little tick mark there. I found one value. This doesn't, that does. 7 fits from 3 to 8. Yep, so 7, I'd put another tick mark. Ooh, that's sloppy. 6 fits, yeah, so I'd put another tick mark. All right, so one way is to, every time you find one, you make 4 tick marks and a slash for the 5th, and we should end up with 10 values in this set of data values. 10 of them should be these values here, 3 to 8. All right, you can do it any way you want to. You can just go through and count anything that's 3 to 8. Let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There's 10 values that are 3 to 8. So that's another way to do it. Is just go through and count as you go. So you can use tally marks if you want, which is what most people do, or you just eyeball it and count and go through there as you want. But you should find that 10 of those values up above fall in between 3 and 8. 9 values, or 9 measurements, were from 9 to 14, and 6 of the measurements were from 15 to 20, 2 of the measurements were 21 to 26, and 3 of the measurements were 27 to 32. So notice that the number of measurements is shrinking. It's going down, 10, down to 9, down to 6, down to 2. And then we had a little hiccup here. We didn't expect it to kind of bounce back up, but that's okay. It's real life data. Sometimes that happens. Frequency, note, just count how many numbers are in this row. All right, use any method. Relative frequency says, okay, these frequency numbers, I need to relate them to the total number here. Now, when you add these all up, you should have 30 values. This sigma symbol here, that stands for summation in math. It just means the sum, or if you add them all up. So if I add them all up, I should get 30. So I checked it. Yes, I did. And I'd usually put a little check mark there to say, yep, that's right. Okay. Frequency, I need relative frequency. I need to take the frequency and relate it to the total number. So 10 in terms of 30, or 10 divided by 30, gives me 0.33. And I'm just going to round all these to 2 decimal places because it looks pretty. 9 out of 30, that's 0.30, or 30%. 6 out of 30, that's 0.20, or 20%, 7%, and 10%. So 33% of these values were 3 to 8, measurements of 3 to 8. 30% of these values were measurements 9 to 14. 20% of these values were measurements 15 to 20, and so on. Notice that the sum of these measurements adds up to 1, adds up to the whole thing. If we're speaking percent, if I'm saying 33%, 30%, etc., they're going to add up to 100%. So if you're speaking percent, you just got to bump the decimal 2 to the right and speak percent. It just depends what language you're speaking. And then finally, cumulative frequency. Cumulative means accumulate. So you just accumulate more and more and more. This is a running total. So how many did we have when we were done with the first row? We had 10 values. Okay. How many did we have when we were done with the second row? Well, we had 10 and we accumulated 9 more. Now we have 19. It's kind of a running total. When we were done with the third row, how many did we have? Oh, we accumulated 6 more measurements, 6 more values. Now we've taken into account 25 values or 25 measurements. Add 2 more. Now I've got 27 measurements, and add the final 3. Now I've got 30 measurements, which should match up to how many measurements or values are in your data, your raw data. So just a couple of notes here to finish it off here. If you're looking for relative frequency, it's just the frequency over the total. All right, we want to compare the frequency to the total. Cumulative frequency, that's just a running total. You start with your first row, and then you just add more values as you go down the table. All right, so now that we have organized our data in a frequency table, we can draw some graphs, and we can kind of see a normal distribution curve taking shape. All right, so let's draw just a frequency distribution graph. I just want a graph of the frequencies. We're going to start out with your class boundaries on bottom. All right, so from 2.5 to 8.5 is going to be our first bar. 8.5 to 14.5 is going to be our second bar, and so on. It's just a simple bar graph. So class boundaries are going to be our measurements on the x-axis on the bottom. Our y-axis, well, you just got to ask yourself what you're measuring. We are measuring frequencies. So if you go back to your table and look at your frequency column, the highest number we had was 10 frequencies in that first row. So make your y-axis go up to 10. You can use any units you want. I went by 2s, 2, 4, 6, 8, 10. All right, so how many values or how many measurements in that raw data fell between 2.5 and 8.5? We had 10 occurred. All right, 10 values were between these two numbers. And just make your little bar go up 10 steps tall. How many values fell between 8.5 and 14.5? We had 9 values, so make that bar go 9 steps tall. In the third row in your table, we had 6 values, so make that one 6 steps tall, and then 2, and then 3. So these are just a measure of the frequencies in the form of a bar chart. Put your class boundaries on the x-axis, and then your frequencies on the y-axis. And if you just use your imagination here, you can kind of see a curve. It's curving downwards, and usually it would kind of level out. But we had a little hiccup there and it jumped up. So a normal distribution curve is kind of taken shape there. You can also look at a cumulative frequency graph. So we're just going to graph the numbers we accumulated in that last column in your table, the cumulative frequency, sometimes called an ogive. So again, on the x-axis, I'm just going to use my class boundaries, but we're not going to do a bar chart this time. We're just going to do a line graph from dot to dot to dot, just to connect the dot graph. So here's my class boundaries. So 2.5 to 8.5. On the y-axis, is whatever you're measuring. So we're measuring cumulative frequency. Go look at your cumulative frequency total and see what the biggest number is. It's 30. So make your y-axis go up to 30 using any units you want. All right, how many values had I accumulated at 2.5? Well, that's my starting point. I hadn't accumulated any yet, so that's on 0. That's 0 steps up. All right. Now, by the time I got to 8.5, from 2.5 to 8.5, how many had I accumulated? Well, that's the first value in your cumulative frequency graph. You had accumulated 10 measurements, 10 values. So that's going to be 10 steps high, connect them with a dot. By the time I got to 14.5, how many had I accumulated? Well, there were 10 here and 9 here, so I'm up to 19 so far. I have accumulated 19, so that's just short of 20. Connect it with a line. All right, by the time I got to 20.5, I had accumulated 25, and then I had accumulated 27, and finally, by the time I got to the end, I had accumulated all 30 values. So cumulative frequency graph is just a graph of the numbers that you accumulated, the values that you had accumulated, the measurements you had accumulated. And as we graph this, you can again see a curve taking shape. So it's just kind of a visual of taking the raw data, organizing it into a table, and creating a graph. And when we do that, these curves appear that we're going to deal with later in the course. Now, some of these curves that appear when you organize your data in a table and then graph it are your basic symmetrical curve. This is the one we like. This is the one we work on the most in this elementary statistics class. In a symmetrical, the mode is in the middle, all right? And by the way, so is the mean and the median, but that's another lesson. A symmetrical curve, even though I'm not a very good artist, is supposed to split right down the middle into two identical halves. So if I have 100 people in the room, and this is the average, or this is the mode, then 50 people should be on the left and 50 people should be on the right out of those 100 people. And this is usually how the data falls out. This is how we like it to fall out. It's called a normal distribution shape, a normal symmetrical curve. But sometimes it just depends on what we're studying or how we're asking the question. Sometimes the data comes out with two modes. A mode means the most common answer, the answer you see the most. Maybe I'm asking a question, a political question, and I have Republicans and Democrats in the same room. Well, the Republicans will answer that question one way, and the Democrats will answer it another way. So I will have two really common answers. I will have two modes, all right? The Republicans, most of them answered this way, and the Democrats, most of them answered this way. Two modes, bimodal. Sometimes that happens, all right? You kind of want to be careful how you phrase your question or your study, because you really want your data to be normally or symmetrically distributed. Now, sometimes we have outliers that play tricks on our graph, and maybe there's a really low person out here kind of pulling the tail of this graph to the left. We say this graph is skewed to the left. And maybe over here we have a really high outlier pulling the tail of this graph to the right. So imagine a symmetrical graph being pulled to the left or stretched to the left or skewed to the left or stretched or skewed to the right. One example is if you try to calculate like the average salary, all right? I like to use teacher examples. Sometimes they'll say the average salary of a teacher is $60,000, all right? And that's never correct. The average salary of a teacher, might be $40,000. But the reason that the average is in the wrong place is because you have your principals and your superintendent's salaries lumped in there with the teachers. Their salaries are much higher than a teacher's salary. So our median, which should have been in the same place as our average, which should have been in the same place as our mode, what most people make, our average or our mean should have been right in the middle. But what happens is when you average the boss's salaries in there with it, your average is now over here. Most teachers, the mode is still here at the peak of the mountain here. Most teachers make $40,000, but these administrators, these bosses, their high incomes are pulling the mean over here. So what the paper reports is, the average teacher's salary is $60,000, when really most teachers only make $40,000. It's those really high incomes that are kind of stretching or pulling that graph to the right, so it's skewed to the right. And really low outliers do the same thing. If I average test scores for my class, maybe the student scored a 0 for reasons, unknown to me. But when I average that 0 into my class average, it makes my class average look bad because most of my students did really well. But the class average is a lot lower. Maybe most of my students scored a 90, but my class average shows up as an 80 because this outlier, this 0 on the test, pulled the average over here. The mode's still here at the top of the mountain, but the average, the mean, is much lower because this outlier pulled the average to the left. Okay, and then finally, I call this the participation trophy graph. If you were in Parks and Rec soccer and you played the whole season and at the end everybody got a ribbon, All right, that's called a participation trophy. Everybody gets a trophy. Basically, it's like giving everybody 100 on the test. So this is called a uniform distribution. Notice there's no curve. There's no mode. Most of the people scored this, but a few scored lower. Let me go back to this. Most of the people scored, an 80%. A few of them scored 70%. A few of them scored 90%. There might be one or two that scored 0. There might be one or two that scored 100. That kind of thing. That's what we expect. But when everybody makes the same grade, everybody makes 100. I should probably put 100 right there. So this is the participation trophy graph. Everybody make 100. There is no mode. There's no most people curve. There's no top of the mountain where the mode is. Everybody made 100. Participation grade, participation trophy. That's called a uniform distribution. All right, guys, I think that's all I got for this one.